Pam, very good. So does everyone have the page that I gave you yesterday that was very useful? Okay, so we are going to use it a little bit more today. And so if you don't have one, sit close to someone that has one. What happens? People don't like this page. They are protesting. Okay.
Certainly look more lovely after you ask everybody explain it. I don't like yesterday in the morning. Oh, also Pedro promised that it's going to be shorter than yesterday, right?
Yeah. Okay. Good. So let's summarize a couple of things that we saw yesterday. So yesterday we said that if we have a stack of D branes and we have string theory, which describes open strings ending on this D brane, and if you ask what's the dynamics of these open strings on this D brane, well, these open strings at low energy, they are point particles because the string tension shrinks the particles, so they are points. So they describe point particles. At low energy, only the massless guys survive. So we only care about massless open strings. Those are the gluons, or the photons normally. But when we have a stack of D branes, we end out the string with a label for the endpoints, and so they become non-abelian, because now it matters which brane they are attaching to. And so we see that the low energy limit of these open strings is a theory in 10 dimensions, which is super Young-Mills. Why Young-Mills? Because we need gluons. And why super? Because there is supersymmetry. So if you start with supersymmetry, you stay with supersymmetry. You did not break any supersymmetry. And now we said that we could go from this 10-dimensional theory. We can do something that sounds interesting. We can reduce the theory and ignore 6 dimensions and go to 4 dimensions and ignore everything that happens on the other 6 dimensions. So things that depend on the 6 dimensions, we don't care. Right? We don't drop fields, but we drop dependence on the 6 dimensions. And so what was before a gluon that had 10 components, now the first 4 are the gluon in 4 dimensions, but the remaining 6 are 6 scalars from a 4-dimensional point of view. The fermions, what was before a spinor that had 16 components, breaks into 8 plus 8 fermions now in 4 dimensions. Okay? And we get some theory that we can write down. We just plug the fields here, we work out all the gamma matrices like we did yesterday, we get some theory. And today, for the most part, we are going to use this bosonic part of the action, not the fermionic part. And that was what? There was f squared coming from 10 dimensions. You just get the f squared. But then, when you take f squared, where some components are in 6 dimensions, some are in 4, you get derivative of scalar. And when both components are in the 6 dimensions, you get just the commutator part of the field strength, because there is no derivatives in the 6th direction. And so it's a theory that it's like a phi to the 4 theory, but with a very specific coupling. It's not any coupling of scalars, right? So we can think of it, it's like a phi to the 4 special theory. It's not any phi to the 4, it's not any coupling, it's this particular commutator to the power 4, right? It's a particular coupling of the form phi m, phi n, phi m, phi n, a plus, dot, 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 right? Or minus the other term squared. Sorry, no, not square. It's the commutator and then square. One of the terms is this. Okay. Now, one thing we could have done is, instead of considering this, we could think that instead we could have done the reduction at this level and think, no, instead, I want to consider the low energy limit of a stack of D3 branes. So from the beginning, I start and I say there are some D3 branes. And there are some open strings here. Right? That's fine. Well, that's the same thing. Instead of first going to low energy and then reducing, here we are first reducing, and then if we go to low energy, we would get to n equals 4 super young meals. So another way of thinking of n equals 4 super young meals is directly the low energy limit of a stack of D3 branes instead of D10 that then go to 3 dimensions. Now, here, to be totally correct, what we should say is the following, is that this stack of branes is like our material, our table, and there are some gluons here that are moving and interacting and so on, right? And what matters are the degrees of freedom on the table. But if we are an experimentalist here on the lab, right, what's important for me is the table. It's electromagnetic interactions. I can see the table, right? And the table can receive and send signals to me. And gravity, right? I can fall. It's bad, right? And so at low energy, if I have the stack of branes, and if I have also some closed strings flying here, what we would get is a theory that describes the table, which is n equals 4 super young meals, plus gravity. And this gravity is decoupled at low energy by the same reason that gravity always is decoupled at low energy. Gravity vanishes at low energy. That's why in the lab, when we do condensed matter, we don't care about our gravitational interaction with it to the table, unless we are very heavy. Yeah.
Can you just motivate a bit more this idea of stacking the branes?
Okay, good. So why did we stack? Why don't I put just one brane, right? Well, putting the stack of branes gave us an non-abelian theory, which was this trace. And being non-abelian gave us a hope that this has something to do with string theory by what we have seen before. So this is one way of motivating. We want to make contact with these large n-gauge theories because the large n-gauge theories have a chance of being related to string theories because at the level of pictures, they are string theories. And so we need a stack of D-branes if we want this theory then to have an alternative description. That's one reason. But the other reason will come tomorrow, where I will say that I want these branes, I want to have many because I want them to back react on the geometry and to have an alternative description. But that is only going to become clear tomorrow. For now, it's a definition. I start with n D-branes, and so I get a theory where all my fields are n by n matrices. But for now, the only motivation we have is because we like fat diagrams. Tomorrow, we will have one more motivation, which is that we will want to engineer a setup where we put some object that is heavy enough to back react the geometry. And for that, one D-brane is not enough, but n of them are enough. Okay? So for now, we stay at the level of definition, and we can motivate it a little bit later.
Pedro,
Yes?
is your string on the second set, can that open string venture into the sixth dimension? No, the other.
This one here?
Yeah. Can it go off the brain?
Yeah, it can point off the brain. And if it does, it's a scalar excitation. If it stays on the brain, it's a gluon excitation. Right? So you should think that when you have a D-brane, excitations that are perpendicular to the D-brane that describe the transverse motion of the D-brane exist, and the longitudinal ones are the massless modes. Right? So the excitations of the string become gluons here, and transverse motion of the brain, which are the scalars here. So these scalars add the interpretation of what are the excitations precisely perpendicular to the brain. That's what happened under the reduction. Okay.
The gravity comes in from the closed strings.
The gravity would come from the closed strings. If I have gravity flying around, I always have this plus decoupled with gravity.
Is it obvious? Closed strings with gravity means I cannot make the connection.
It's obvious that closed strings give gravity and open strings give gluons.
Yeah, something like that.
That's true. And it's obvious if you did string theory. If you did not, you can just take it as a true statement. It's a statement that open strings at low energy, they have spin 1 particles. Closed strings at low energy, they contain spin 0 and spin 2. And the spectrum of strings is, the closed strings include the gravitons.
Just a comment there. Last homework on string theory is compute the spectrum of the closed strings, and then you can actually see the gravitational.
Okay. Now, here now we have this theory. And one thing we could do is repeat the type of analysis we did for the ON sigma model and compute the one-loop beta function of this theory. This is just a one-loop computation. You just do some computation. If you do the effect of the gluons, is what we wrote already before. But you can do the effect of the scalars and the fermions. You can add what do the fermions and the scalars do. And whenever you have, here it's n, not n squared, n. Whenever you have scalars, they come with a contribution n over 6. And whenever you have fermions, here there are okay, so let me see. So there are this contribution times 6 from the scalars. Here you would put normally the number of scalars. And if you have fermions, the result that you would put here is plus, let me see, there are 4. Yeah, plus 2/3 of n times 4. And these are the, no, I think it's probably 1/8, probably like this. And this would be the number of fermions. Or plus 4. Number of two-component fermions that have there are 4 with alpha, 4 with alpha dot. And if there is no mistake, this should be 0. Okay? Now, this doesn't tell you the theory is conformal. It tells you the theory is classically conformal, and at one loop it stays conformal. But this did not prove that this is just a one-loop computation at one loop. So I would like to give you a flavor of the argument about why this is a true statement to all loop orders. Okay, I was going to review something here, but I think it's not important. Okay. Good. So that's where supersymmetry will come about. And what we are going to do first is note that we have this theory. It has some obvious symmetries. And one of the obvious symmetries of this theory, one symmetry, right? One symmetry that relates to these scalars is SO6, right? If I rotate the scalars, nothing matters. In this picture, there is rotation of these 6 orthogonal directions, right? XM. And so these scalars, there is a symmetry that rotates phi m into lambda mn phi n, where this is an element of SO6. And in particular, this SO6, which as we saw is the same as SU4, and as Justin explained, okay, there might be some there are some Z2s, right? But okay, for us it's the same as Z4, as SU4. But what matters is that these guys, it contain 3 U1s, which are called the Cartan. These are the number of elements that commute with each other, that you have inside the group that commute with each other, that define the U1. In SU2, you can say that you have SZ, right? That tells you the spin Z component. And then, knowing SZ, then you have the other states in the representation by acting with S plus and S minus. Right? So the Cartan is just SZ. It's just the U1 generated by the SZ. But here we can define 3 analogs of SZ that commute with each other. So let's do it. Let's define these 3 U1s. So I can do the following. I can take my scalar phi1 and phi2 and consider rotations that rotate the 2 of them. Right? This is clearly an SO2, which is a U1 that just rotates the two of them. Right? So this defines an SO2, rotations of these two, or U1. Right? Very explicitly, here is a nice way of writing it. You can say that phi1 plus or minus I phi2, if you make this complex combination, this is nice because then rotations are just a statement that this quantity transforms as E to the plus minus I theta times the same quantity, phi1 plus minus I phi2. So all the cosines and sines, etc., can be encoded in this simple relation. Can you read? Careful, can you read? It looks like hard to read. Can you see properly? It's okay? Is it visible? Okay. And so you have this rotation. In other words, this object here, if we call one of them Z, let me call Z to be phi1 plus I phi2, and Z bar to be phi1 minus I phi2, which, by the way, remember before, yesterday we said that we could trade, if we wanted, phi m, we can replace by this phi AB. We can either use the vector index, or we can use two fundamental indices, and it's the same thing. If you were to work it out, this guy would be, if I remember correctly, phi 3, 4, I think. With some choice of sigma matrices to convert one to the other, this would be phi 3, 4. But fine, so we have this definition of Z and Z bar. Then we would say that this object is a charged scalar, while phi1, the full thing is a charged scalar, whereas each of them, this phi, was neutral. It was just a neutral scalar. But now this combination, we say it's a charged scalar of charge plus 1, meaning that you pick the plus sign under the transformation under this U1. Right? Z transforms into E to the plus I theta Z. Whereas Z bar, this would have charge minus 1. Well, more precisely, this is one U1, but there are three U1s, right? You can see right away other two that you could construct that commute with this one, right? Which is the other one, the other two U1s you could construct? One rotates scalar 1 and 2, and the other 3, 4, and 5, 6, right? So we could have another U1 corresponding to phi 3 and phi 4 rotations, and another U1 corresponding to phi 6 and phi 5 and phi 6 rotation. Okay. Then it's better that we would have a U1, and so this minus 1 and this plus 1. Maybe it's smarter to put a minus 1 and put minus 1, 0, 0 to indicate that we are talking about the first U1. Right? And then we could define some scalar here, x, to be phi 3 plus I phi 4, and similarly for x bar. And then this guy would have charge 0 plus 1, 0, right? Because it has charge under the second U1. And finally here, we could define some y that would be phi 5 plus I phi 6, and some y bar that would be phi 5 minus I phi 6. And then these y's would have charge 0, 0, plus 1. Whereas where these three labels are the values of the three cartons. Now that we define this object that has charge 1, charge is interesting because charge is conserved. So we like constructing objects with charge, because once you construct an object with just charge 5, right? A correlation function, if you have one operator with charge 5, and with dot, 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 the dot, dot, dot better have charge -5, otherwise the result is 0. Right? Because if you transform the correlator, this picks e to the 5 theta, this picks whatever it picks. If it's a symmetry, it must be the same. Otherwise, you get a 0, right? Because you get correlator equal to something else times correlator, so correlator is 0. Right? And so charge is conserved. And so these operators, now that we define some charge, we can define operators that have n units of charge. So now we define the operator O with j units of charge at some point x. Let me define this operator as saying that I have trace of z times z times z times z, etc., times z, where this, multiply this guy, j times. Right? This z is a matrix, and I multiply this matrix field, boom, 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 j times. Or I can write it, it's equivalent, as trace of z to the power j. And this object here now, of course, has charge j. This charge, by the way, is called R charge. And this symmetry, SO6, is called R symmetry. Just the name of this symmetry.
Good question.
Yes?
Is it specifically like the first one is R charge, or is it the whole 3 tuple?
The 3. All this symmetry, everything that is related to this SO6 is called R symmetry, and the corresponding charges are called R charges.
Right, but if I had Y's instead of Z's, for example, that
They would have j units of R charge. You would say this is an R charge. We can say J1. And then that would be J2 and that would be J3. But they are all charges. Okay? So it has j units of R charge, this operator.
All the z's are evaluated at same x.
Good. Excellent point. They have to be. I forgot to say, but they have to be. Why do they have to be evaluated at the same x? What would go wrong if they were evaluated at different x's?
Non-local operator?
It would be a bit non-local. But non-local operator, it's okay. I love non-local operators. That would not be a big deal, but there's something worse.
would be a symmetry.
Sorry?
It wouldn't be a symmetry.
It would be a symmetry. It would not be a symmetry. This is also not a symmetry. This is an operator. For what you
I meant like the rotations you're doing are like at different points, so you could have something not cancel out, right?
What symmetries are you talking about?
The R symmetry.
No, R symmetry, no. R symmetry just rotates everyone globally, right? It's our global symmetry.
Okay, so it's gauge symmetry.
Gauge symmetry, right? So these are all, it's very important, all fields at the same location. This is crucial. And this is required by gauge symmetry. Namely, each field chi, if I have chi, and chi is one of the fields that we made this list with oscillators last time, so it can be any of the list. Let me write them down. dk of f, it can be dk of psi, it can be dk of phi. In particular, k can be 0, and then it's what we are discussing. It can be dk of psi bar, and finally, it can be dk of f bar. So any of these fields transforms under omega of x times chi times omega minus 1 of x. And so gauge invariant operators, that implies that trace of one such field at position x times one other field at position x times another field at position x dot 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 is a good gauge invariant operator. All right, so if we want to deal with gauge invariant operators, right, operators that don't depend on our choice of gauge, which are physical operators, we should take these building blocks. These, we can call them, these guys, we can call them letters, and construct operators by putting several letters together and making words. So each operator is a word made of these operators. In particular, this is a very boring word. Zzz. It's when you sleep. Okay? It means sleeping. Okay. Now, we observe here an interesting thing, that this operator has charge J. And what is the dimension of this operator? Or more precisely, what's the classical dimension of the operator? What's the dimension of one scalar?
4D, it's 1.
1. So what's the dimension of this operator?
J.
J. You have J scalars, so dimension J. And so this operator has something interesting. It has the dimension is equal to the R charge. Right? That's a true statement. Classically, the dimension is equal to the R charge. Now, it turns out that when this happens, this is equal to the R charge. If this happens, this implies that the dimension is equal to J at the quantum level as well. In other words, it's J plus 0. There are no quantum corrections. It stays like this. And that's what I'm going to explain now. So the idea is that there are some these are special operators in the theory. So let's first have in mind that we have the following. We have the space of operators. These are operators of my theory. Right? Some of them are local, some of them are non-local. Right? So then there is a big space inside, which would be the space of local operators. Then these operators, in a conformal theory, we split operators into two groups. Remember? Primaries that are more important and descendants. So then we have the group here of primaries. To go from primaries to the other ones, to the descendants, I just apply momentum and I get to the other ones. But our theory is super conformal. So primaries are operators that K kills, right? Right? K decreases dimension by 1, but we have a super conformal theory. And so we have super primaries here. Inside this, we have the super primaries that are the operators that S and S bar kill, where these are the super generators that are roughly the square root of K. And we could now define inside some operators that we are going to define now that are called chiral super primaries, whose definition is that some of the Q's, kill them. Okay. So let's look, and then we will see that these chiral superprimaries are a special group. They will have the property that these operators have the delta is equal, this dimension of these guys is protected. By this, it means there are no quantum corrections. Okay. And then what we will see, so this is what we are going to show first. And second, we will see that the Lagrangian of our theory is equal. It's not one of these operators. It's not one of these chiral primaries. But it's some symmetry transformation, like acting with some Q's or something, and some S's acting on this chiral primary. And this symmetry transformation just raises or lowers dimensions by alpha integers or integers. And so we will argue that this also, the Lagrangian, has no quantum corrections. Therefore, the dimension of the Lagrangian is just 4, and therefore the beta function is equal to 0. Right? Because the beta function not being 0, like we argued last time, was the statement that the Lagrangian acquires a quantum dimension. So that's our goal. And then we learn the beta function is 0, and we learn that n equals 4 is not just classically conformal, but n equals 4 is a CFT. Or the super conformal CFT. Okay. So let's start with writing the condition. So we want that Q alpha A acting on our operator O at the origin is equal to 0 for some A and alpha, or some charge. And in particular, because the operator is a superprimary, it's killed by S and S bar. So this implies, because we are in this group of superprimaries, that okay. Oof. Okay. That the action of Q alpha A with S B beta on O of 0 equal to 0. Right? Because if we act first with S, we get 0. If we act first with Q, we get 0. But this combination here, by the algebra, remember these were the last algebra relations we wrote. If you look at the page, this is the 1.7 in the page we have, that I'm going to write in this better notation with SO4 indices. With SO4 indices, we get something like the rotation matrix with index BA times epsilon alpha beta. That's the first term instead of using the sigma matrices. Then the second term plus would be some rotation M alpha beta times delta BA. And the last term would be minus a half of epsilon alpha beta delta AB times D. Okay, up to some factors of 2 and i's and so on. Right. And you would have this commuting with the acting on the operator O. But that's the algebra. Now this guy we can ignore if we consider O to be a scalar. Right. Then rotations are irrelevant. And then what do we get? We get that the rotation acting on my operator, this rotation, needs to be, if it should be equal to the dimension acting on my operator. Right? And so we get that this condition is equivalent to the condition that the commutator of R dA with O is equal to delta times O times delta BA. Or sum A and alpha, it implies this condition. And now we see that indeed, if I have my operator O, which is built of this scalar phi 3, 4 many times, phi 3, 4, phi 3, 4, etc. Right? Then this is just, you remember with oscillators, we say that we create index 3 and we create index 4. We do this at position 1. Then we create index 3, create index 4 at position 2, etc. Until create index 3, create index 4 at position j, acting on the vacuum, which is now like a tensor product of j vector.
Could you raise the board a little?
Yeah, we can't see it behind the podium.
Thanks.
Right? So the O here would be obtained like this. And we can easily check that the rotation acting on this vector, that some rotations will kill the state and some will work. So let's see. This is our operator there. What's the rotation operator? R BA. Well, it's something like this. You create operator. It's written. I think it's written in the page. You create index B. You annihilate index A, and you make it traceless because it's an element of SU4. So you subtract minus 1/4 of delta BA C dagger C C dagger C. Right? It's just to make it traceless, to make it a generator of SU4. And now you can imagine acting with R. If I choose A to be 1, B on our operator O, then let's see what will happen. First, if you have A is 1, so first if B is 1 or not 1, it matters that this term is there or not there. So let's first consider that B is 3 or 4, right? Then what you do is or anything. A is 1 and B is not 1, so you only have this term. But A is 1. You have annihilation operator with index 1. right? But your field has no one with 1, right? And so immediately this gives 0 if B is not equal to 1, right? Just because C1 acting on vacuum equal to 0, right? What you need is something like C1, C dagger 1 acting on vacuum is equal to vacuum when you use the commutation relation, right? But if the oscillator acts on the vacuum right away, you give 0. So this is working. Now you just need to check what happens when B is equal to 1. So if B is equal to 1, and then if B is equal to 1, then we only care about this term, because this one we saw that because we have this C1, it always kills the state. So we only care about this one. And this one, if you have 3 and 3, you count how many 3s you have. If you have 4 and 4, you count how many 4s you have, right? And so in total, you just measure the number of fields. So you get number of 3s, number of 4s, divided by 1/4. So you get something like minus 1/2 times J times the state O if B is equal to A.
Pedro, I think you should erase that dagger at the end of C.
Ah, of course. Thank you. Yeah, so C dagger C is the number, right? So I act with this operator, I act on all possible sides, it just measures how many 3s there are and how many 4s there are, because I sum over 3 and 4. And so it gives me something like minus J over 2. Okay, it's just a question of convention, I'm not sure. Yeah, probably here. So I assume we want to get minus delta over 2. I was not careful with 2's, but the 2's should be such that whatever I get is what I want to get. Okay? And so the conclusion is that indeed, the operator we did, it has this property that is annihilated by some Q's. But this means that I start with my operator, and normally I would act with some Q's. Let me put 4 arrows because we have like n equals 4, so we could have like a bunch of options, right? And then we would have here a bunch of operators that have dimension delta plus 1/2. And then I would go here and act with a bunch more operators. I could also act directly with some times, with some k, but I would act more and so on and get the next level. That would be delta plus 1 if I start with delta and so on. And this defines a representation that is infinite dimensional and that has more and more operators at each level. But what we see now is that sometimes these arrows don't exist. So they might, these arrows might be absent. Right? Because Q kills the state. So these Q's, some of these Q's, in our case, the Q's with index 1 and 2, which were half of them, kill the state. And now we lost some of the states. Now we only have this. And then we continue and we have this and so on. But we got, when this happens, we get what's called a short representation. A short representation has a smaller dimension, it's smaller. And that if you rotate your states with supersymmetry, they rotate in that smaller subspace. Right? Now, this is a topological quantity. What's the dimension of your representation? It's into how many people you can transform, right? It's something, it's a number. So you cannot deform continuously and change that number. Right? So if you are in a small representation, you stay in a small representation. This argument is a little bit subtle. There is a caveat to it. If someone finds the caveat, I can answer. But for a first approximation, it's a true state. Yeah, if you find what's the subtle point in it, you can tell me and I can agree or not. But when you have a representation, the representation is smaller. It's smaller because delta is equal to the R charge. That made the representation smaller. And so if delta is equal to the R charge, the representation becomes smaller, but then it cannot move. It cannot suddenly become long again. And so once you have a condition that delta is equal to the R charge, because that condition is responsible for the shortening of the representation, that condition must stay. And so delta equal R charge cannot receive quantum corrections, and therefore delta is equal to the R charge, and that's it.
Could you repeat the last part?
Everything. So I was saying that delta equal to J implies we are in a short representation. But being in a short representation implies we stay there. Right? Because we are transforming under smaller operators, we are not suddenly going to move discontinuously to a bigger representation. And so if we stay there, it means that delta is equal to J always. And so if you start classically with delta equal to J, we continue with delta equal to J. Okay. So in particular, trace of z square as dimension 2. Yeah.
How did we? So I agree that it's going to be a representation with delta equals J. How do you know it's going to be the same representation? Like, what if it's like another branch on that structure? Like, how do you know you're not going to start mixing branches, so to speak?
Okay, I'm not sure what you have in mind. So let me say what the subtle point could be, and maybe you tell me if that's what you have in mind. What could happen is that there is something in group theory called recombination of representation, which is you could have accidents where actually there is a small representation and there is another one that's small, and they have exactly the right size that they can marry into a big representation.
Yeah, I was imagining like, you have that left half and that right half, and both of those exist, and then together they form a long representation or something.
Well, but then it's a bit tricky because this operator cannot appear twice, right? So, but you could have things like that, you could somehow, the representation could be just right to recombine. So then you have to make sure, okay, those pesky accidents happen or not. And they could happen, and sometimes they do. But they don't, for what we care. But that's really a super subtle detail. That's the most subtle detail about recombination of short representations into long representations. But that will take like 2 lectures just to discuss that. I don't want to do it. It could happen, but the argument is cute. It works. You can believe it, and then if you find an exception, you can try to see if there is some recombination going on. So in particular, this guy, it's one example. It has R charge 2. It has dimension 2. So this stays with dimension 2. And this implies that the following one that I'm going to write that looks totally different also has dimension 2. So let's write it. It's trace. Okay, let me write first one that is maybe easier. Phi I, phi j minus 1 over 6 delta ij phi k phi k, trace of this. This guy also has dimension 2, again plus 0, no quantum corrections. This one is simple. The reason why if this has dimension 2, this has dimension 2 is because they are in the same representation. So they are actually the same. You can rotate this one into this one. Let's see how that works in a simple way. So remember that these scalars, I took 2 scalars, right? Each of them was in the vector representation, right? So I took a 6 and I multiplied with a 6. I take 2 vectors. What can I build representation-wise? when I take two vectors? What representations can I get from a two-vector product of two-vector representation?
Symmetric part, anti-symmetric part.
Symmetric and anti-symmetric is almost okay, but you can split a little bit more. Trace. First trace, 1 plus. Next. Trace is 1. That's the singlet representation. It has dimension 1. The next one. One of the ones that you said.
Symmetric.
Symmetric and traceless.
Yeah, symmetric.
What would be the dimension of that one? The anti-symmetric is a bit easier. Let's do the anti-symmetric first. Anti-symmetric. How many components? 15. You agree? If they have the index, it's that corner there. That's 15. So how many are missing? 20, right? So this 20 is called a symmetric traceless. And so if you are symmetric traceless, then you are in the same representation. Right? This is symmetric traceless because you see, trace phi I phi j is the same as phi j phi I, so it's symmetric by definition, right? And it's traceless because I subtracted the trace. So if I contract the indices, I get 0 because I constructed it to be traceless. Right? So this is symmetric traceless. Do you agree?
But
This one is also symmetric traceless. Let's see it more explicitly. Because what's this guy? This guy is trace of phi 1 plus I phi 2 square. Do you agree? This is the definition of Z. But this is nothing but trace of phi 1 square minus trace of phi 2 square plus I times trace of phi 1 phi 2 plus phi 2 phi 1, right? The second, these are just the same term, right? The last two are the same. So this is clearly symmetric. And this is traceless because this cancels with this, right? In other words, this is equal to some matrix chi ij trace phi I phi j, where what is this matrix? This matrix is 1 minus 1 I. So it's clearly traceless and symmetric. Do you agree? And so they are both in the same representation, which is symmetric traceless, so they are the same. You can rotate from one to the other. Okay. So there are two scalars, they can only be in the, so this is in the symmetric traceless as well. By the way, these 6 times 6, we can call them 1, 15, 20, but actually sometimes if someone else had already used 20 or some other representation, you needed to put a prime here. And this is how everyone knows these operators in the field. They are the 20 prime. So if someone has the 20 prime, it's this or this. And everyone knows the 20 prime. No one knows what the 20 is because the 20 appeared in some paper and then it was irrelevant afterwards. But everyone knows what the 20 prime is, and the 20 prime is the trace of Z squared. Okay, so that's just historical. And another operator, if you want to write this in a notation where we trade the index I to this index AB, this operator would look like this. It would be trace. We trade this index by phi AB, where these are SU4 indices now. We trade J by phi CD. Okay. Now here we need to contract them. So let's write the contraction. We have phi, one field is A prime, B prime. One field is C prime, D prime. How do you contract these indices? So in SO6, we have delta function, right? We just contract, just make them equal. And in SU4, how do I make a singlet out of these 4 indices? If I have SU4 symmetry? Sorry? With epsilon, exactly. So this is the same as this contraction. It's epsilon A prime, B prime, C prime, D prime. And similarly, this delta is just epsilon A prime, B prime, C prime, D prime. And the equivalent of 1/6 is minus 1/24.
So it's supposed to be ABCD on the second one.
Of course. And so this operator as dimension 2. So now we can go and remember that this operator is a bunch of oscillators, right? And now we can act, we have dimension 2. So how many Qs do we want to act to get something that has dimension 4? 4 Qs. So let's act with 4 Qs. So we have this operator here. Let's call it O, A, B, C, D. Okay. And so let's act with 4 Qs on this O, A, B, C, D. A, B, C, D. So let's act first with a Q that eats the index A and gives an index alpha. Right? So we act with this Q. Then let's act with a Q that it takes the index B and will give an index beta. Then let's act with a Q that takes the index C and gives alpha, beta, gamma, an index gamma. And finally, let's act with a Q that takes the index D and gives delta. And to get rid of all indices, let's then contract the result with alpha, beta, gamma, delta.
How are we choosing the commutator and decommutator?
It's just the usual action, right? So if you act on something that's bosonic, it's commutator. Now this is a fermionic object, so you act with an anticommutator.
Okay, I see.
Now it's a bosonic object, you act with commutator, and then it's a fermionic object, you act with anticommutator. Okay. So what happens? What happens is that this operator here, remember how to think of it. It just removes index A and adds index alpha. Right? And this guy, we have 4 Cs in total, right? 4 C daggers. Because we have 2 operators, each of them with 2 Cs inside our O. So what happens after we act with all these Qs? Q, 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 Q. What can happen to the Cs? To these C daggers that we start. We start with this object, right, that has dimension 2, and it has 4 C bars, and we act with 4 times these Qs. What happens from the point to the Cs and the C bars and the C daggers?
Each Q removes the C.
Each Q removes a C, so after acting with all the Qs, how many Cs do I have? 0. So at the end we have 0 Cs, and how many A daggers? 4. So this is equal to curly F squared. Which will be the object that would have in one position 2 A daggers and in the other position 2 A daggers. You could do it carefully with oscillators and so on. You would see that this would be the case. But just based on the counting that we saw yesterday, it had to be this.
Do we need B daggers as well?
No. Remember, F alpha beta was A dagger alpha, A dagger beta acting on the vacuum. And so we get precisely the self-dual part of the field strength square. See, and so we conclude that this object has dimension 4. This is enough. Okay. In the review, he shows that with F bar also, but this is enough. Why? Because now this guy is one of the elements of the Lagrangian. I can write this Lagrangian, this trace of F square. I could write it as trace of curly F square plus trace of F bar square. And now I show that this guy has dimension 4. But everyone in the Lagrangian is related to each other by supersymmetry. And so the coefficient of this guy must be the same as the coefficient of the scalars, the coefficient of the fermions. They are all locked to each other. If one changes, everyone needs to change because they are related by supersymmetry. And so if we show that this coefficient doesn't move, no, which is this, then G doesn't move. And so we just showed this implies that L has dimension 4. And the beta function is equal to 0. And the argument here is supersymmetry.
Pedro, that's
Yeah.
probably 2 epsilon. In your giant operator, it's probably 2 epsilon. At the very end of your giant operator. Big. Yes, that line. No, up.
Here?
At the end,
Here at the end, let's see.
there should be 2 epsilon because it's alpha beta. It should be epsilon, alpha, beta. Epsilon.
Yeah. Why did I write this? Actually, let me think. I think I don't need this. Yeah. What is the relation in the notes? Yeah, you are right. It's with the 2 epsilons. Yeah, but I don't need. If I don't put the epsilons, I think. Okay, just to be sure. But I'm not one. It could be. No, maybe it needs to be like this. Let's put the epsilon. Epsilon, alpha, gamma, epsilon, delta, delta. Then you get this contracted with the appropriate epsilon. But still, it's precisely the combination that appears in the Lagrangian, and therefore, the Lagrangian cannot move, and the beta function needs to be 0. If I stop here, I think I will reach ADS-CFT in the last lecture of the ADS-CFT course, and that's it. That's fine.